Welcome, dear students, to the course of Analysis of Algorithm. This is our week number 8, and in this lecture, I will talk about the analysis of another very efficient and useful algorithm which is called the merge sort. Before starting today's lecture, let me revise briefly what we have studied in the previous week. If you remember, in the previous week, we studied about the analysis of selection sort algorithm. And as I mentioned in the previous week, selection sort algorithm, like the bubble sort algorithm, is a comparison based sorting algorithm. And like the bubble sort algorithm, it is also inefficient on large list. What does it mean? That you can use selection sort for small amount of data. However, once the list or the data become larger, it become inefficient. Like the bubble sort algorithm, the selection sort algorithm was also a simple sorting algorithm. And the basic technique of the algorithm is like this: that first you have to find the minimum value in the list. Once you find the minimum value in the list, you have to swap that value with the element at the first position or at the first location. And then you have to repeat the process for the remainder of the list. We studied the theoretical aspect of the selection sort algorithm in the previous week, and then we saw general examples as well as animation of the selection sort algorithm. And then we did a dry run of the selection sort algorithm, how it works, how it sort data, what are the different steps of the algorithm, and how they work. And finally, we analyze the algorithm. During the analysis of the selection sort algorithm, we concluded that the worst case analysis and the best case as well as the average case analysis of the selection sort algorithm provide us the same value, the same running time, and that is n square. In today's lecture, we are going to study another algorithm, that is the merge sort algorithm. So we are going to start our lecture first by highlighting the objectives of this lecture, what we are going to learn at the end of this lecture. After that, after the discussion of the objectives, I will talk about the divide and conquer approach. If you remember, our assignment number 1 was about the different types of algorithms. For example, we have different types of techniques available for algorithm, like the simple recursive algorithm, the backtracking algorithm, the dynamic programming algorithms, the greedy algorithms, branch and bound algorithms, brute force algorithms, and randomized algorithm. One of them is the divide and conquer approach based algorithm. The simple and recursive algorithm, they involve a function which call itself directly or indirectly again and again. In a similar way, the backtracking algorithm solves the problem recursively by trying to build a solution incrementally, but one piece at a time. On the other side, the technique used by the dynamic programming algorithm is to go for optimization. Wherever we see a recursive solution that has repeated calls for same input, we can optimize it by using the dynamic programming algorithms. And then we have the greedy algorithms, which build up a solution part by part, or you can say piece by piece, that always choose the next piece that offer the most obvious and immediate benefit. And also we have the branch and bound algorithm, which is used for solving combinational or combinatorial optimization problems. The problems that can be typically that involve exponential or exponential terms in regard of the time complexity. And the brute force algorithm is a straightforward method for solving a problem. Similarly, we have the randomized algorithms, which actually uses the random numbers to decide what to do next anywhere. So we have the randomized approach as well. And finally, the algorithm approach, which is very much efficient, is known as the divide and conquer approach. So this was a brief background. So the divide and conquer approach is actually one of the available techniques that we used for the algorithms or to classify the algorithms. So we have the simple recursive algorithm, the backtracking algorithms, dynamic programming, greedy branch and bound algorithms, brute force algorithm, randomized, and the divide and conquer based algorithm. So what is divide and conquer approach? We have to study it in today's lecture. And then after that, we will see introduction to the merge sort algorithm, which is actually based on the divide and conquer approach. So we will see the theoretical aspect of the merge sort algorithm and also the pseudocode of the merge sort, means the algorithm itself. And then we will analyze the merge sort algorithm. But before analyzing the algorithm, we have to see how we can actually analyze the divide and conquer approach based algorithms. So after that, we will analyze the merge sort algorithm. So let us start with the objectives, the general objectives for this lecture. So as I mentioned, today's lecture is about merge sort algorithm. So at the end of this week, you will be able to understand the basics of the divide and conquer approach. You will also be able to learn how the merge sort algorithm or pseudocode actually works, how it sorts data, what are the different steps in the algorithm, and how the divide and conquer approach can be applied to the merge sort algorithm. And finally, you will be able to analyze the running time, or more specifically the worst case running time analysis of the merge sort algorithm. So let us start with the divide and conquer approach. Many useful algorithms, they are actually recursive in nature or recursive in structure. What does it mean? It means that in order to solve a given problem, they actually call themselves recursively one or more times to deal with closely the related subproblems. Divide and conquer approach is actually an approach which is used by many useful algorithms. I will mention some of the examples here. For example, the binary search algorithm is actually based on the divide and conquer approach. Similarly, the merge sort algorithm that we are going to study in this lecture is actually based on the divide and conquer approach. And also the quicksort algorithm, which is going to be the topic for our next week, is also based on the divide and conquer approach. And also we have other solutions like the towers of Hanoi and fractals. They all are examples of the divide and conquer approach. They're actually based on the divide and conquer approach. So you can say that many useful algorithms, they are recursive in nature. Recursive in nature mean that they actually use the divide and conquer approach to solve the problem. Now, what is divide and conquer approach? Okay, useful algorithm use them, but what it is, how it solve the problem. So the technique, which is the divide and conquer approach, actually involves 3 steps. So all the algorithms that typically follow the divide and conquer approach, they actually follow 3 steps. In some of the books, the 2 steps are merged together. So you can say they actually involve 2 or 3 steps. But the classical way of divide and conquer approach is that they solve the problem by using 3 different steps. What are these steps? So the basic step is to divide the problem into a number of subproblems. The subproblems are going to be the smaller instances of the same problem. You can say that divide the problem into simpler version of itself. Or a problem is divided into several subproblems which are going to be of the same type and ideally about the equal size, almost equal size. So the first step of the divide and conquer approach is to divide the problem, and then the second step is to conquer the subproblems by solving them recursively, and the third step is to combine the solution to the subproblems into the solution for the original problem. So here we can see these steps one by one in detail. The first step is the divide step, in which we divide the problem into a number of subproblems. The subproblems are the simpler version of the main problem, or they are smaller instances of the same problem. So by using the divide and conquer approach, you can actually divide the problem into several subproblems of the same type. The type must be same. And also the division occur in a manner that both of the subproblems will contain equal amount of elements, or you can say the size are going to be equal of both the subproblems. So one of the main step of the divide and conquer approach is to divide the problem. The second step of the divide and conquer approach is known as the conquer. Conquer the subproblems mean solving the subproblem recursively. What does it mean? So in the conquer step, we actually solve the subproblems recursively. You can say the conquer step actually happen recursively. And the third step of this process is the combine step. Mean after solving the subproblem, you have to combine the solutions to the subproblems into the solution for the original problem. So combine the solution to the subproblems into the solution for the original problem. That is the third step of the divide and conquer approach. Or you can say that in this step, we can combine the results of the simpler version. Remember, in the divide step, we divided the problem into subproblems, while in the combine step, we actually combine the result of the simpler version to form your final solution. So that is like opposite of the divide step. In the divide step, we actually divide the problem, while in the combine step, we combine the solution to the subproblem to form the solution to the original problem. So here we have to combine the results. We can also graphically represent the divide and conquer approach like this. So here you can see the three steps. First, we have a problem which is given to us, and we want to solve the problem by using the divide and conquer approach. So once you have the problem and you want to apply the divide and conquer approach, the first step is to divide the problem into subproblems. And here you can see, remember, we have to divide the problem in such a way that both the subproblem will contain almost equal elements, or the sizes of the two subproblem must be equal, and you can see them here. So we have divided the given problem into two subproblems. That is the first step. What is the second step? The second step is the conquer. You have to solve the subproblems. So here we have to solve the left hand side subproblem, and here we have to solve the right hand side subproblem. That is the second step. And conquer here mean, as we are dealing with the sorting algorithms, so if you apply the merge sort algorithm over this problem, it will means to sort them out in either ascending form or descending form. So once you solve the problem, the final step is to combine the solution of the subproblems to form the solution for the main problem. So here you can see we actually solve the main problem, but not directly. First we divide the problem into subproblems, then we solve the subproblem recursively, and finally we combine the solution. So these are the three main steps of the divide and conquer approach. And now it's time to elaborate to shed some light on the merge sort algorithm. First, we need to understand the theoretical aspect of the merge sort algorithm, and then we will see the pseudocode, and finally the dry run and analysis. So let us start with the introduction of the merge sort algorithm or the theoretical background. Merge sort algorithm is one of the most efficient sorting algorithm. The algorithms that we have studied until now, like the bubble sort algorithm, the insertion sort algorithm, and what was the third one? Yes, the selection sort algorithm. These three algorithms are not that much efficient because their running times are n square and n. While merge sort algorithm as compared to the previous three algorithm is much more efficient, especially if the list given to us is larger. You can say it is efficient over large list of items, much more efficient than the previous algorithm. And why? Because we will see in the analysis that the running time of the merge sort algorithm is log n. If you remember the running time of the algorithms that we saw in the comparison, like we did a comparison of the running time of the algorithms like n square, n cube, n, and then we saw exponential and the constant, and one of them was the log algorithms. So the running time of the algorithms which contain the log function are actually efficient algorithm. So merge sort is an efficient algorithm as compared to the previously studied algorithm because the running time of this algorithm is log n, and log is a function which grows very slowly over the input, right? So that is why it is an efficient sorting algorithm, especially if the list is a large list. And the merge sort algorithm is the perfect example that follow the divide and conquer approach. If as I mentioned that majority of the efficient algorithm, they are actually they actually follow the divide and conquer approach, like the quick sort, merge sort, towers of Hanoi, fractals, and binary search. All these are based on the divide and conquer approach. So merge sort actually is a perfect example of the divide and conquer technique or approach. It means that merge sort will also follow the three-step approach that we just saw in the divide and conquer approach. So merge sort, first it will divide the problem, then it will conquer the sub problems, and finally it will combine the solution of the sub problems. Now how the merge sort algorithm actually works. The merge sort algorithm will repeatedly break down a list into several sublists, or you can say it will divide the main problem into several subproblems repeatedly. But we need to stop this repetition, we need to stop this condition. Up to how long it will repeatedly break down the problem into subproblems? We need a threshold. We need a condition where this should stop subdivision, where it should stop subdividing the problem into sub problems. Or you can say the list, we need to stop the division of the list into sub problems. Actually, once the sub list contain a single element, it's an indication that now it is time to stop dividing the problem into several sub problems. Like for example, you have 4 elements in a list, divide them into 2 sublists, each having 2 elements. And then in the next step, divide each sub list that have 2 elements into further sublist which will contain only 1 element. So once each sublist contain a single element, now it's time to stop the division here. And then you have to conquer and merge those sublists in a manner that will result into a sorted list. If this is not clear to you at the moment, don't worry. The concept will become clear to you when we start examples on merge sort algorithm. Things will become more clear. Now, as we just saw that the merge sort algorithm itself is based on the divide and conquer approach. So it has to follow the three-step approach. The first step is divide step. And the divide step actually means that you have to divide the problem or the list into subproblems. For example, you have a list or array, and the list or array has n elements. So what will happen in the divide step? You have to divide it into two subsequences. Each one will contain n by 2 elements. So for example, if the size of n is 6, then each sub list will contain 6 by 2 will give you 3. So there is 3 element. 3 element on the left hand side while 3 elements on the right hand side. Now you must be thinking, what if there are 7 elements, odd elements, or what if there are 9 elements, or what will happen if there are 11 elements, and so on. So the solution is that in that case, when we have odd number elements in the list, you have to take the floor function or the ceiling function. Means that one side will contain one more element from the other side. For example, if you have 5 elements and you divide the list into two parts, then one of the portion will contain 3 elements while the other will contain 2 elements. Normally we take floor function, but you can take the ceiling function as well. Doesn't matter. One element doesn't matter. Okay, so you have to divide the n elements into subsequences, each with n by 2 elements, half of the element of the original array. So you can say that in the divide step, we actually split the given array into two halves. But how it will happen? It's very simple. As we know from the binary search, we need to find the midpoint of the given array. And for that, we actually uses a formula which is very simple, like a bit technical, that is lower bound of the array plus upper bound of the array and divided by 2, and then finally take the ceiling or floor function. It will give you the midpoint. But the simple is that if you have 12 element, then the midpoint is going to be like 6 or 7. If you have 13 elements, then the midpoint is going to be 6 or 7, things like that. If you have 14 element, then the midpoint is going to be 7, and so on. Okay, so we have to split the given array into two halves. How we will do it? We have to find the midpoint of the array by using the formula, and the formula is that lower bound plus upper bound divided by 2. Now what is lower bound and upper bound? I'm sure you must be familiar with it if you know about the concept of array. Like the first index of the array is actually our lower bound, while the last index of the array is actually our upper bound. It could be sometime the lower bound could be 0, sometime it could be 1. Normally we started the indexes from 1 in case of algorithms, while if you are using the programming code, then you have to start the indexes from 0. So as I mentioned that if the array has 6 elements, then the merge sort algorithm will break it down into two sub-arrays with 3 elements each. Now suppose we have to sort an array, and the array has been represented by the letter A. So a sub-problem would be sort a subsection of this array. So in that case, we will need some indexes like pointer variables, which will point to the locations of different elements stored in the array. For example, index P, it will refer to the first element, location of the first element, and index R will actually refer to the location of the last element of the array. So if you have 10 elements in the array A and you started the indexes from 1, then P will refer to 1, location number 1, while R will refer to location number 10. And we can denote it by by the expression like this: A represent the name of the array, P is the starting index, and R is the final index. So if a given array A has only a single element, then remember, if you have a single element, it is already in sorted form. And such a case is known as the base case, where the array has only a single element. So it does not need to be sorted as it is already in sorted form. However, if you do not have a single element, then you have to split the array, which is mentioned by APR, into two sub-arrays. And remember, we have to find the midpoint of the array. So suppose we need a third index, and suppose that index is represented by Q. So Q is the index which actually refers to the mid location of the array. So now we have three indexes. Index P refer to the element stored at the first location. Index R refer to the element which is stored at the last location, while the index Q, which actually refer to the element stored in the middle. So now we need to split this array into two sub-arrays. The first sub-array will contain elements starting from P and ending at Q, while the second sub-array will contain elements starting from Q plus 1 and ending at R. And each of the sub-array will contain half of the elements of APQR. What does it mean? Let us put some number. Consider the array A has 10 elements. So P will refer to the index 1, R will refer to the index 10. Once you divide the array into two sub-arrays, then the first sub-array will contain elements from P to Q. Here Q is 5, the mid element. So 1 to 5, this is going to be array 1. And then Q plus 1 mean 5 plus 1, that is 6. Then A 6 to 10 will contain the elements of the second sub-array. And they are going to be like the same element, half element on the left hand side and half element on the right hand side. So you see that is how the divide step actually happen in the merge sort algorithm. And then the second step of the merge sort algorithm is the conquer step. Here we have to sort the two subsequences recursively by using the merge sort itself. So you see I am using the word recursively here. Means you have to apply the merge sort algorithm again and again in order to solve the subsequences or sublist or subproblems. So what does it mean? It means that we need to sort both the subarrays that we saw on the previous slide, represented by A, P up to Q, and the second subarray PQ plus 1 up to R. So we need to sort them out in the conquer step, or we need to solve this problem in the conquer step. Once you have solved this problem, now it's time to combine them, which is the third step of the merge sort algorithm. So in the combine step, we actually merge the two sorted subsequences to produce the sorted array. So if you think on the divide and conquer approach, it actually say that divide the problem and conquer the solution. And then you have to combine the solution. Sorry, conquer the problem and combine the solutions. So if you compare our if you consider this example again of the array using indexes p, q, r, it means that we have to combine the element bake in the array, which was a, p, r. That is the initial array. How we will combine it? We need to merge the sub arrays, the two sub sorted arrays, which we saw, and which we represented by a, p up to q, and a, q plus r up to 1. So you have to combine these two arrays into a sorted sequence. Remember, these two arrays, sub arrays, or sub problems, or subsequences, are sublisted. They are already in sorted form. Here in the combine step, we just need to combine the solution of these sub problem to the solution of the main problem or the original problem. So the recursion bottoms out when the sequence to be sorted has length 1, in which case there is no work to be done since every sequence of length 1 is already in sorted form. If you doesn't understand what I say, let us see with the help of this example. Here we can actually see an example which demonstrates how the merge sort algorithm sort out the data. We are given with a problem with the data which is in unsorted form, and we are asked to sort this data by using the merge sort algorithm. So first thing that you need to do is to split this problem into two subproblems, to split this array into two subarray, to split this list into two sublists, to split this sequence into two subsequences. So for that, we need to find the midpoint. You see, here is our midpoint. It could be 3, it could be 4. So the midpoint is a point so that it divides the given problem into subproblems so that each of the subproblem will contain almost same elements, or the sizes must be the same. So here you can see 4 elements on the left hand side while 4 elements on the right hand side. Now recursion, so we need to subdivide the problem again into subproblems. So here now we have 4 elements. Division will give us 2 elements on one side and 2 elements on the other side. Again, consider this array and recursively divide it again. So we will get 1 element on the left side and 1 element on the right side. Now, remember, we have to stop the process of division once we get a single element, which is called the simple case or the base case. And here you can see. So we have reached a situation where we have only one element in the subarray. So we need to stop here. Okay, this is the base case. So the base case has been reached out. It's time to stop here. Okay, now it's time to conquer and combine the solution. As I mentioned, some authors will combine the merge and conquer step into one step. So here you can see we are actually going to merge the solutions of the subproblem to form the solution to the main problem. So here you can see we have to combine 1 and 5 in such a way that they give us a sorted sequence. We have to combine 8 and 3 in such a way so that they give us a sorted sequence. We have to combine 4 and 2 in such a way so that they give us a sorted sequence, and similarly 1 and 0. After that, you have to recursively apply the same thing. Merge these two subsequences now in such a way that they give us a sorted sequence, and similarly here. Finally, you have to combine the solution of the last two subarray to form a solution to the final subarray which was in unsorted form. So at the end of this step, you will see that the array is now in sorted form, which was in unsorted form at the beginning of the problem of the process. So we have sorted out the given list of items into by using the merge sort algorithm, and we saw this through the help of a general example. If you see a more technical example, let me show. I have a technical example as well. Yes, here it is. So again, if you see, there is the same problem. However, we have applied the merge sort algorithm. First, we see that we can see that the merge sort algorithm is called for the left hand side, and then it is called for the right hand side, and again we have called it for the left hand side and then for the right hand side, and then again for the left hand side and the right hand side, up to how much time we need to call it. Once we reach the base case, which mean each subproblem will contain only one element. So once that case has been reached, we need to stop out. We need to stop then. So we have to stop here once we reach the base case. We will not go into the detail of this this example, as we have already seen an example, what we are interested in is the merge sort algorithm itself. So let us see how the merge sort algorithm will actually work, or how it will actually sort out our data. Okay, so the merge sort algorithm. We are going to explore the pseudocode of the merge sort algorithm in a while, but before going to see the pseudocode, it's important to highlight some variables, some indexes that we are going to use in the algorithm. And it is also important that one of the key operation of the merge sort algorithm is the merging of the two sorted sequences in the combine step. And here you can see divide step is not that much complex. Conquer step is not that much complex. The actual operation happens in the merge step. Once we have two sorted sequences and we want to combine them to form a sub-solution, or a solution that is closer to the main solution, we need to merge them. So merging is an important operation and it plays a critical role in the merge sort algorithm. How it works, we have to see the pseudocode in a moment. So remember, the key operation of the merge sort algorithm is to merge the two or more than two sorted sequences in the combine step. Now, to perform the merging, we actually need to use a procedure, a function, and we will represent this procedure, this function, with a name known as merge. So this is not the merge sort algorithm. This is actually a function. This is actually a procedure which will help us to sort out the data by using the merge sort algorithm. So this is not the actual algorithm. This is actually the key operation of the merge sort algorithm. Or you can say that this is a helping procedure which will help us to combine the solution of the sub problems, right? So this is actually a procedure, or you can see this is a part of the merge sort algorithm, not the complete merge sort algorithm. So it is a function which we will rely on in order to sort out our data. So two things. Key operation of the merge sort algorithm is actually the merging step. Second point is that we actually need an auxiliary function procedure which will help us in the merging step, and that is known as the merge. And A is actually name of the array, and remember P, Q, R are the indexes. The first, the location of the first element, R is the location of the last element, while Q is the midpoint that we have just calculated by using the ceiling or floor function. Okay, we also have a condition that P is always going to be less than or equal to the mid, and mid is going to less than the final value. Okay, so the procedure, as we saw in the example, the procedure which is part of the merge step actually assume that the sub arrays are already in sorted form, and we already sorted them in the concur step. What does it mean? It means that, okay, I will combine the elements of the two sub arrays, for example 1 5 and 3 8, but I need them to be in sorted form. So we can see 1 5 is already in sorted form, while 3 8 are already in sorted form. Now the merge auxiliary procedure will combine these two sub procedures, but the condition is that they must be in sorted form. So this is mentioned here, that it will merge them into a single sorted sub array, right? But the condition is that they must be in sorted form. Okay, something related with the analysis of the merge sort algorithm, we will see it in a moment, but it is important to note it here as well, that the merge procedure actually takes theta n time. This function, it actually takes n time. And you know what is n? N is actually the total number of elements, and it could be calculated by a formula like r minus p plus 1, or simply you can say that n is the size of the array. So the merge procedure actually will take, as we will see in the analysis as well, will take only theta n time. Okay, how the merge the merge procedure actually combine the two sub sorted arrays. To understand that, remember I give you an example in the insertion sort algorithm, the way we play a game by using the playing card. The card are face down on the table, but this time we are actually dealing with two piles of the card. One pile on the card, one pile of the card, for example the left hand side, and the second pile of the card, for example on the right hand side, and they are face up on a table. So each pile is actually sorted. You know, this is also in sorted form, and this is already in sorted form. So we also know that on this pile, the smallest card is on the top. Similarly, here the smallest card is on the top. So here the smallest card is 1, which is on the top of the pile. And here the smallest card is 0, which is also on the top of the pile. Now, we need to perform an operation. And the operation is that we wish to merge the two piles into a single sorted output file, which is here, the final step. Okay, so our basic step consists of choosing the smallest of the two cards. You see, here we have the smallest card, the value is 1, and here we have the smallest card and the value is 0. So once you compare these two cards which are on the top of the two piles, you came to know that 0 is actually less than 1. So you have to place this card here. Or in other words, you have to select this card from this pile. There is 0. So removing it from its pile, once you remove this, what will happen? It will exposes a new top card, and now the value of this card is 1. You see, now we have a 1 here and 1 here. Oh, both are equal. So that is up to you whether you want to place this card here or this card here. That is up to you, or the algorithm will decide. So normally we have to choose the card from the left hand side, which is 1. And now this will expose another card that is 3. Now here on the top we have 3, while here on the top we have 1. Once you compare the two cards on the top of each pile, we come to know that 1 is less than 3. So we will remove 1 from this pile and will place it here. What will happen? It will expose the next card, which is 2. So here you have to remove the 2 from this pile and place it here. It will expose the next card, which is 4. So now you have to compare 4 with the 3. 3 is less, so remove it from this pile, place it here. Compare 5 with 4. 4 is less, so remove it here, place it here. Oh, one of the pile become empty. So once the pile become empty, it's time to remove the other cards from the other pile one by one. So we have 5 left, remove it, and then we have 8, remove it and place it here. So finally you will see that the list is in sorted form. So this is generally what I tried to explain, that how actually the merge procedure will help us to merge the two sorted arrays. So we take an example of the playing cards in which we suppose that there are two piles. They are already in sorted form. They are placed on the table and we wish to combine them. So we have to take card from each pile which is at the top, and then we need to compare them and remove the card which is having the smallest value and placing it on the final solution. So we will see that our merge sort algorithm, which actually contains a merge procedure which plays a critical role, an important function, is actually which the pseudocode is also mentioned here. So this merge function actually implements the idea that I just discussed. What was the idea? That it will actually consider that we have two piles of cards. It will compare the two cards on the top, and it will take the card having the smallest value and will place it in another array. So that is the basic functionality of the merge procedure or function that we will see in a moment. Okay. Once more thing is that one more thing is that we need a condition. How we will come to know that one of the pile has become empty, right? As we saw here, this pile become empty before this pile. So in the pseudocode, how we will handle this situation? For example, either pile is empty in a basic step. So for that purpose, in order to deal such situation, we have to place a special card at the bottom of each pile, which is known as a sentinel value. We will cover it in a moment. The infinity symbol here is actually a sentinel value, an indication that the list is now, the pile is now finished. We have no more cards on this pile. So actually this is a special value that we use to simplify our pseudocode. So here we use the infinity as the sentinel value. Okay. So whenever a card with this sentinel value is exposed, it cannot be the smaller card unless both piles have their sentinel cards exposed. Once it happens, once we reach the sentinel value, once we reach it on either side of the pile, all the non-sentinel cards, it is an indication that all the non-sentinel cards have already been placed onto the output file. Okay. So actually this is an indication that stop removing. We don't have any more cards on this pile, so please remove the cards from the other piles and place them on the output file. Okay, so this is going to be a special value which will indicate the end of the pile, you can say. Okay, so this is something which we are going to use in the merge sort pseudocode. So let me revise the basic things that we are going to rely on in this merge procedure. One thing is that it is actually the basic operation of the merge sort algorithm is the merging or combining the two sorted sequences in the combined step. And then for that, inside the algorithm, the merge sort algorithm, we actually need to rely on an auxiliary procedure function which is known as the merge, and A is the name of the array, PQR are the indexes of the array, and we have to call this procedure in order to combine the two sorted array. But we need to a supposition, and the supposition is that the merge procedure will be applied on the subproblems that are already in sorted form, and it will combine them into a single output file, into a single sorted array. Okay, and finally we have to deal with a special sentinel value that is represented by the infinity sign here, which actually represent the end of each sub array. And I also explain the concept how the merge procedure will work out, how it will work in the pseudocode by an example from the playing cards. So this was about the pseudocode. In the second half of this lecture, I will start from here. We will study the merge sort algorithm, especially the merge procedure in detail, and we will also we will give a dry run to an example by using the merge sort algorithm. So let us take a short break and we will back in a moment. Once we return, we will study the merge sort algorithm, and actually we will apply it on an example on unsorted data, and we will try to sort the data by using the merge sort algorithm, but we will be focusing more on the merge procedure rather than the merge sort algorithm. So let us see how it will work. Let us take a break. We will be back after a short break.